Tonight, we're going to explore something that sounds simple but reveals one of the most profound truths about our universe. Everything spins. But when you start to understand why nothing can stop spinning, when you truly grasp what keeps this cosmic rotation going, it changes how you see motion itself. If you find this kind of deep exploration interesting, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now let's begin this journey into the heart of spinning worlds. Let's start with something you can see right now. Step outside on any clear night and look up. Every point of light you see is spinning. The stars rotate on their axes. The planets wheel around those stars. Even the galaxy itself, that faint river of light stretching across the sky, is turning slowly through space. This isn't coincidence. This is the universe revealing something fundamental about the nature of motion itself. But here's what most people don't realize. This spinning isn't just happening. It can't stop happening. There's a principle operating throughout the cosmos, from the smallest particles to the largest structures we can observe, that ensures rotational motion persists across billions of years. It's called conservation of angular momentum, and it's one of the most powerful and universal laws in physics. Angular momentum is the rotational equivalent of regular momentum. Just as a moving object tends to keep moving in a straight line, a spinning object tends to keep spinning. But unlike linear momentum, which can be stopped by friction or obstacles, angular momentum is extraordinarily persistent. Once something starts spinning, the universe provides very few ways for it to completely stop. Think about this for a moment. The Earth has been spinning for over 4 billion years. Every single day of your life, every day in all of human history, every day since life first appeared on this planet, the Earth has completed one rotation. It's never missed a day. It's never slowed down significantly. It just keeps turning, carrying us through space at over 1,000 miles per hour at the equator, and we barely notice. Why doesn't Earth's rotation slow down and stop? Why don't all the spinning objects in the universe gradually wind down like toys running out of energy? The answer lies in the mathematics of rotation and the deep structure of physical law itself. Angular momentum depends on three things: how much mass is spinning, how fast it's spinning, and how far that mass is from the center of rotation. These three factors combine in a specific way that makes angular momentum incredibly stable. But more importantly, angular momentum is conserved. In the absence of external forces, the total angular momentum of a system cannot change. It cannot be created or destroyed, only transferred from one object to another. This conservation law operates everywhere. When an ice skater pulls her arms in during a spin, she's not adding energy to her rotation. She's redistributing her mass closer to her center, which forces her to spin faster to conserve her angular momentum. The same principle that makes the skater spin faster is what shaped our solar system and continues to govern the motion of galaxies billions of light years away. You don't need to fully grasp the mathematics to appreciate the scale of this principle. Just let the universality settle for a moment. Our solar system began as a vast, slowly rotating cloud of gas and dust. This cloud was enormous, extending far beyond the current orbit of Neptune, perhaps even beyond Pluto's path. But it had angular momentum. Even the slightest rotation in that primordial cloud meant that momentum had to be conserved as gravity pulled the material together. As the cloud collapsed under its own gravity, conservation of angular momentum transformed it. The cloud couldn't just fall straight toward the center, because that would violate the conservation law. Instead, it began to flatten into a disk, spinning faster and faster as it contracted. The material that would become our sun gathered at the center, while the outer regions spread into the thin, rotating disk where planets would eventually form. This process explains one of the most striking features of our solar system. All the planets orbit in nearly the same plane, and they all move in the same direction around the sun. This isn't coincidence. It's the signature of angular momentum conservation written across the architecture of our cosmic neighborhood. But there's something puzzling about our solar system that reveals just how complex angular momentum can be. The sun contains over 99% of the mass in the solar system, but it holds only about 1% of the total angular momentum. Most of the rotational motion is actually in the planets, especially Jupiter, which, despite being much smaller than the sun, carries more than half of the solar system's total angular momentum. This distribution seems backwards at first. You might expect the most massive object to have the most angular momentum. But angular momentum depends not just on mass, but on distance from the rotation axis. Jupiter, orbiting far from the sun, carries enormous angular momentum, even though it's much less massive. This is why the conservation of angular momentum during solar system formation led to a slowly spinning sun surrounded by rapidly orbiting planets. The early sun actually faced a problem because of this. As the solar nebula collapsed, the material falling toward the center carried angular momentum with it. If all that material had simply merged with the forming sun, our star would be spinning much faster than it actually does. Something had to remove angular momentum from the collapsing material, allowing it to fall into the sun. The solutions involved magnetic fields threading through the rotating disk. These fields acted like invisible brakes, coupling the spin of the forming sun to the orbital motion of the surrounding material. Angular momentum was transferred outward through magnetic forces, slowing the sun's rotation while accelerating the disk material that would become the planets. This magnetic braking process allowed our sun to form without spinning itself apart, while preserving the total angular momentum in the orbital motion of the planetary system. The same process is happening throughout the galaxy right now. Wherever new stars are forming, angular momentum conservation is shaping the outcome. Every star begins with a rotating disk of material around it, and many of these disks will form planetary systems of their own. The flat, rotating structure is inevitable whenever material collapses under gravity while conserving angular momentum. As you listen, notice how difficult it is to actually picture the scales we're discussing. The solar nebula that formed our sun and planets was larger than our current solar system, yet it condensed into the compact arrangement we see today. The timescales involved stretch across millions of years. The angular momentum that shaped this process has been conserved for over 4 billion years and will continue unchanged for billions more. The persistence of rotation extends far beyond planetary systems. Galaxies themselves are vast spinning structures, rotating once every few 100 million years. Our own Milky Way galaxy is turning slowly through space, carrying billions of stars in a grand rotation that has continued for over 10 billion years. The angular momentum locked in this galactic rotation is staggering in scale, representing the combined motion of hundreds of billions of stellar systems. But galaxies don't just rotate as solid objects. Different parts move at different speeds, creating spiral patterns that sweep through the disk over time. The spiral arms you see in pictures of galaxies aren't fixed structures. They're waves of star formation that rotate through the galaxy at their own speed, separate from the motion of the stars themselves. This differential rotation creates some of the most beautiful structures in the universe, but it also reveals the deep persistence of angular momentum. Even as galaxies collide and merge, even as they're stretched and distorted by gravitational interactions, their total angular momentum remains conserved. The spinning motion is transferred and redistributed, but never lost. When galaxies do collide, the process takes hundreds of millions of years to complete. Throughout this cosmic dance, angular momentum governs the outcome. The merged galaxy that results will carry the combined angular momentum of both original systems. Computer simulations of galactic mergers show material being flung into long tails and streams, but these apparently chaotic structures still follow the strict rules of angular momentum conservation. Our local group of galaxies is itself slowly rotating. The Milky Way and Andromeda galaxy are approaching each other, but they're not moving in a straight line. Their mutual gravity has given them angular momentum relative to each other, and when they merge in about 4 billion years, this angular momentum will shape the structure of the resulting galaxy. It's normal if this feels abstract. Physics often lives beyond intuition. We evolved to understand objects moving at walking speeds across distances we can see. The idea that invisible principles govern motion across galactic scales, preserving rotational patterns for billions of years, challenges our everyday understanding of how things work. Yet this same principle operates in your daily life in ways you might not notice. Every time you ride a bicycle, you're relying on angular momentum conservation. The spinning wheels resist changes to their orientation, helping you maintain balance. When you turn, you're redistributing angular momentum between different axes of rotation. The earth beneath your feet is a massive gyroscope, spinning with enough angular momentum to resist any attempt to change its orientation. This rotational stability is what gives us consistent seasons and a stable climate. Without angular momentum conservation, Earth's axis might wobble chaotically, making complex life nearly impossible. Even the atoms that make up your body contain spinning particles. Electrons have an intrinsic angular momentum called spin, even though they're not literally spinning like little tops. This quantum mechanical angular momentum follows the same conservation laws as the rotation of planets and galaxies. From the smallest scales to the largest, the universe preserves rotational motion with extraordinary consistency. This conservation operates across time scales that dwarf human experience. The rotation that shaped our solar system began before Earth even existed. The galactic rotation that carries us through space has been ongoing since before the first stars formed. Angular momentum connects us to the deepest history of the cosmos, preserving patterns of motion that stretch back to the universe's youth. The mathematics of angular momentum reveals why rotation is so persistent, but the deeper mystery is why this conservation law exists at all. It emerges from the fundamental symmetries of space and time, from the fact that physical laws remain the same regardless of orientation. This deep connection between symmetry and conservation is one of the most profound insights in physics, linking the abstract mathematics of rotation to the concrete reality of spinning worlds. Tonight we've begun to explore how angular momentum conservation shapes the universe from the smallest to the largest scales. But we've only touched the surface of this cosmic principle. There are phenomena in the universe where angular momentum conservation creates effects so extreme they challenge our understanding of what's physically possible. The most extreme examples of angular momentum conservation occur in places where matter itself reaches its limits. When massive stars exhaust their nuclear fuel, gravity wins a final decisive victory. The star's core collapses in less than a second, compressing matter to densities that make atomic nuclei touch. In that collapse, something extraordinary happens to the star's rotation. Consider a star 20 times the mass of our Sun, rotating once every few days. When its core collapses to form a neutron star only 20 kilometers across, conservation of angular momentum compresses not just the star's matter, but its rotation. The same amount of angular momentum that once turned a star larger than Earth's orbit now spins an object the size of a city. The mathematics are straightforward, but the result defies intuition. If you could somehow shrink the Sun to neutron star size while conserving its angular momentum, it would spin roughly 10 billion times faster than it does now. A neutron star formed from our slowly rotating Sun would complete a full rotation in about 1,000th of a second. It would spin nearly 1,000 times per second. Real neutron stars discovered throughout our galaxy confirm these predictions. The fastest known neutron star rotates 716 times per second. At its equator, the surface moves at roughly 15% the speed of light. These objects push matter to the very edge of what's physically possible. Spin them any faster, and the centrifugal forces would overcome even the incredible gravity holding them together. You can picture a neutron star as a cosmic lighthouse, sweeping beams of radio waves across space with each rotation. When those beams happen to point toward Earth, we detect regular pulses of radio energy. Those pulsars, as they're called, are among the most precise timekeepers in the universe. Their rotation is so stable that astronomers use them to detect gravitational waves and test Einstein's theories of spacetime. But even neutron stars aren't the ultimate expression of angular momentum conservation. That distinction belongs to black holes, where the collapse continues beyond the neutron star stage. When the core of an especially massive star collapses past the neutron star limit, nothing can stop the gravitational collapse. All the matter falls toward a mathematical point called a singularity, surrounded by an event horizon from which nothing can escape. The angular momentum of the collapsing star doesn't disappear. It becomes a fundamental property of the black hole itself, warping space-time in ways that would have seemed like science fiction just decades ago. A spinning black hole drags the very fabric of space and time around with it, creating a region called the ergosphere, where nothing can remain stationary relative to distant observers. Black holes can spin at nearly the speed of light. When matter falls into them from companion stars, the accretion process can spin them up to incredible rates. The black hole at the center of a distant galaxy, called NGC 1365, rotates at roughly 87% of the maximum speed allowed by Einstein's relativity. At that rate, its event horizon completes a full rotation in just a few minutes. These spinning black holes power some of the most energetic phenomena in the universe. Jets of plasma, accelerated to nearly light speed, blast outward from the poles of actively feeding black holes. These jets stretch across thousands of light years, carrying energy equivalent to the output of billions of stars. The power source is the black hole's rotation itself, gradually extracted through complex interactions between magnetic fields and the warped spacetime around the spinning event horizon. As you contemplate these extremes, notice how conservation of angular momentum connects the gentlest motions to the most violent events in the cosmos. The same principle that governs a child's spinning top also determines the fate of collapsing stars and shapes the structure of spacetime around black holes. The persistence of rotation extends beyond individual objects to the large-scale structure of the universe itself. Galaxy clusters, containing thousands of individual galaxies, show organized rotation on scales of millions of light years. Even these vast assemblages of matter conserve angular momentum as they evolve over billions of years. Dark matter, the invisible substance that makes up most of the matter in the universe, also participates in this cosmic dance of rotation. Computer simulations of cosmic structure formation show vast halos of dark matter rotating slowly through space, their angular momentum helping to shape the distribution of visible galaxies we observe today. The cosmic web itself, the largest scale structure in the universe, shows hints of rotation. Filaments of galaxies stretching across hundreds of millions of light years may be slowly turning, though the rotation is so gradual that it takes sophisticated analysis to detect. These motions preserve angular momentum imparted during the earliest moments of cosmic history, when quantum fluctuations in the primordial universe seeded the structures we see today. Current observations suggest that some galaxy clusters show signs of coherent rotation, their member galaxies moving in organized patterns that reflect angular momentum conservation on unprecedented scales. If confirmed, these observations would reveal that rotation, governed by conservation laws, operates even on the largest structures the universe has managed to create. The timescales involve stretch human comprehension. The rotation we observe in distant galaxy clusters began when the universe was young, perhaps when it was only a few billion years old. That rotational motion has continued unchanged for most of cosmic history, and it will persist long after our sun has exhausted its nuclear fuel and faded to darkness. When astronomers measure the rotation curves of distant galaxies, they're observing angular momentum that was established billions of years ago. The outer regions of these galaxies move too fast for the visible matter alone to hold them together, leading to the discovery of dark matter. But the rotation itself, the organized circular motion of stars and gas, reflects angular momentum conservation operating across cosmic time. This persistence reveals something profound about the nature of physical law. The universe doesn't forget. Patterns of motion established in the cosmic past continue to influence events today. The angular momentum locked in galactic rotation connects us to the early universe in a direct, measurable way. Even our local group of galaxies carries angular momentum from ancient interactions. The Milky Way and Andromeda galaxy are not simply falling toward each other under gravity. They're engaged in a complex orbital dance, their approach modulated by angular momentum acquired over billions of years of gravitational interaction. When these two galaxies merge in roughly 4 billion years, their combined angular momentum will determine the structure of the resulting system. Computer simulations suggest the merged galaxy will be a large elliptical system, its stars scattered into a roughly spherical distribution. But the details of this transformation will be governed by conservation laws that ensure no angular momentum is lost in the collision. The merger itself will take hundreds of millions of years to complete. Stars from both galaxies will be scattered into new orbits, but the total angular momentum of the system will remain exactly constant throughout the process. Individual stellar orbits may change dramatically, but the combined rotational motion of all the stars will follow the iron law of conservation. As these cosmic events unfold, smaller systems embedded within the galaxies will conserve their own angular momentum independently. Planetary systems like our own will continue their orbital motions largely undisturbed by the galactic merger. The Earth will keep spinning, the planets will maintain their orbits, and the asteroid belt will preserve its collective angular momentum, even as the larger galactic environment transforms around us. This nested hierarchy of rotating systems reveals the scalable nature of angular momentum conservation. From the spin of fundamental particles to the rotation of galaxy clusters, the same principle operates at every level of organization in the universe. Each system conserves its angular momentum independently while participating in the larger rotational motions of the systems that contain it. Quantum mechanics adds another layer to this story. Even individual particles carry intrinsic angular momentum called spin, though it's not rotations in the classical sense. Electrons, protons, and neutrons all have spin, and this quantum mechanical angular momentum is just as conserved as the rotation of planets and stars. The total angular momentum of any isolated quantum system remains constant, linking the microscopic world to cosmic scale phenomena through the same fundamental principle. It's worth pausing to consider what this universality means. From the smallest scales we can probe to the largest structures we can observe, angular momentum conservation operates without exception. No physical system has ever been observed to violate this conservation law. The principle appears to be woven into the fundamental structure of reality itself. This conservation emerges from the rotational symmetry of space. Physical laws remain the same regardless of orientation, and this symmetry automatically leads to angular momentum conservation through deep mathematical connections first understood in the early 20th century. The fact that rotation persists throughout the universe reflects the underlying geometric properties of spacetime itself. But there's something almost mysterious about how this abstract mathematical principle manifests as concrete physical phenomena. The rotation of galaxies, the spin of neutron stars, the orbital motion of planets all follow from the same conservation law. Yet these diverse phenomena seem to emerge from the mathematics as if the universe were solving equations in real time. You don't need to understand the mathematical details to appreciate the profound implications. The universe operates according to principles that ensure certain quantities, including angular momentum, can never be lost. This conservation creates a kind of cosmic memory, preserving patterns of motion across billions of years and vast distances. Every rotating object you can observe, from the Earth beneath your feet to the most distant galaxies visible in our telescopes, carries angular momentum that connects it to the cosmic past. The spin of our planet preserves angular momentum from the solar nebula that collapsed to form our solar system. The rotation of the Milky Way preserves angular momentum from the dark matter halo that collapsed to form our galaxy billions of years ago. This temporal persistence of rotation gives the universe a kind of historical depth that extends far beyond human timescales. The angular momentum we measure today in astronomical objects is the same angular momentum those objects possessed millions or billions of years ago. In this sense, studying rotation allows us to probe the ancient universe directly. Current observations are pushing our understanding of angular momentum conservation to new limits. Gravitational wave detectors can measure the spin of black holes billions of light years away, revealing how angular momentum behaves in the most extreme gravitational fields the universe can produce. These measurements test our understanding of general relativity and probe physics in regimes impossible to study any other way. The recent discovery of gravitational waves from colliding black holes has opened a new window into angular momentum conservation. When two spinning black holes spiral into each other, their individual angular moment combine and partially convert into gravitational radiation that carries energy and angular momentum away from the system. The resulting merged black hole has precisely the angular momentum predicted by conservation laws, confirming these principles operate even in the most violent events the universe can produce. These observations reveal that angular momentum can be transported across the universe by gravitational waves themselves. The collision of two neutron stars 130 million light-years from Earth sent ripples through spacetime that carried away angular momentum, reducing the total spin of the merged system by exactly the amount radiated away in gravitational waves. As detection methods improve, astronomers are beginning to map the distribution of angular momentum throughout the observable universe. Galaxy surveys reveal how rotation correlates with mass, environment, and cosmic history. These observations are painting a picture of a universe where angular momentum, established in the cosmic past, continues to influence structure formation and evolution today. Perhaps most remarkably, the total angular momentum of the observable universe appears to be very close to zero. While individual objects and structures carry enormous amounts of angular momentum, these rotations seem to be distributed in such a way that they nearly cancel out when summed over the largest scales. This suggests that the universe as a whole may have emerged from an initial state with little or no net rotation. Yet this apparent cosmic balance emerges from countless individual systems, each conserving its own angular momentum with exquisite precision. The dance between local conservation and global balance reveals the universe operating according to principles that ensure both stability and complexity across all scales of space and time. Tonight, we've followed angular momentum from its manifestation in everyday objects to its role in shaping the largest structures in the cosmos. But this exploration has revealed something deeper than just another physics principle. It's shown us a universe where nothing is truly forgotten, where patterns of motion established in the ancient past continue to influence events today, and where the same laws that govern a child's spinning top also determine the fate of colliding galaxies. Galaxies. The story of angular momentum becomes even more extraordinary when we consider how it operates in places where our everyday understanding of matter breaks down completely. There are objects in the universe so dense that a teaspoon of their material would weigh as much as a mountain. These are the neutron stars, and they represent perhaps the most extreme demonstration of how the universe preserves rotational motion under the most violent circumstances imaginable. Picture the life cycle of a massive star. For millions of years, it burns steadily, converting hydrogen to helium in its core, maintaining a delicate balance between the inward pull of gravity and the outward pressure of nuclear fusion. The star rotates slowly, perhaps once every few weeks, its vast bulk turning gently through space. But nuclear fuel doesn't last forever. When a star 20 times more massive than our Sun exhausts its nuclear reserves, something catastrophic happens. Without the outward pressure from fusion reactions, gravity wins decisively. The core collapses in less than a second, compressing matter to densities that make atomic nuclei touch. Protons and electrons are crushed together to form neutrons, creating a ball of nuclear matter only 20 kilometers across. This collapse happens so quickly that light itself barely has time to escape the star's surface before the core has already transformed into something entirely new. In that fraction of a second, conservation of angular momentum performs one of its most dramatic demonstrations in the universe. The star's original rotation, spread across millions of kilometers, suddenly becomes concentrated in an object the size of a small city. The same angular momentum that once turned a stellar giant now spins a neutron star at rates that challenge the very limits of what matter can withstand. A neutron star formed from our slowly rotating sun would complete a full rotation in about a millisecond, spinning nearly 1,000 times per second. Real neutron stars throughout our galaxy confirm these extreme predictions. Astronomers have discovered neutron stars rotating more than 700 times per second. At these speeds, the surface of the star moves at roughly 15% the speed of light. Matter at the equator experiences forces millions of times stronger than anything we encounter on Earth, yet the star holds together through gravitational forces so intense they warp space-time itself. You can observe these cosmic lighthouses indirectly through their radio emissions. As a neutron star rotates, it sweeps beams of radiation across space like a cosmic lighthouse. When those beams happen to point toward Earth, radio telescopes detect regular pulses of energy, marking each rotation of the distant star with clockwork precision. These pulsars, as they're called, are among the most accurate timekeepers in the universe. Their rotation is so stable that astronomers use them to detect gravitational waves rippling through space-time. The regularity of their pulses reveals how precisely angular momentum is conserved even in these extreme environments. Any change in the star's rotation rate would be immediately apparent in the timing of the radio pulses. Some neutron stars spin even faster through a process that demonstrates how angular momentum can be transferred between objects across vast distances. When a neutron star exists in a binary system with a normal star, material from the companion can fall onto the neutron star's surface. This accretion process acts like a cosmic engine, gradually spinning up the neutron star to incredible rotation rates. The infalling material carries angular momentum with it, and this momentum must go somewhere. As matter spirals inward through an accretion disk, it transfers its rotational energy to the neutron star, gradually accelerating its spin. Over millions of years, this process can revive dead pulsars, spinning them back up to rates of hundreds of rotations per second. These millisecond pulsars represent some of the most precisely rotating objects known to exist. Their angular momentum has been carefully accumulated through eons of accretion, each particle of infalling matter contributing its tiny portion of rotational energy to the growing spin of the neutron star. But even neutron stars have limits. Rotate them too quickly, and centrifugal forces will overcome the gravitational binding that holds them together. The fastest observed neutron stars appear to be approaching this theoretical limit, spinning at rates where the physics of matter itself prevents further acceleration. As you contemplate these extremes, notice how conservation of angular momentum operates across scales that dwarf human experience. The neutron star's rotation preserves patterns of motion that began when its parent star first formed from a collapsing cloud of gas and dust. That original angular momentum, established billions of years ago, now manifests as the precise rotation of an object more dense than an atomic nucleus. Beyond neutron stars lie even more extreme objects where angular momentum conservation pushes the very structure of spacetime to its limits. When the core of an especially massive star collapses beyond the neutron star stage, nothing in the known universe can halt the gravitational collapse. The result is a black hole where matter disappears behind an event horizon and angular momentum becomes a fundamental property of curved spacetime itself. Black holes can spin at rates approaching the speed of light. Unlike neutron stars, which are held together by the strong nuclear force, black holes are bound only by the geometry of spacetime itself. This allows them to achieve rotation rates that would tear any material object apart. The angular momentum of the collapsing star doesn't disappear when the black hole forms. Instead, it becomes encoded in the very structure of space and time around the event horizon. A spinning black hole creates a region called the ergosphere, where the rotation of the black hole drags space-time itself around like honey being stirred by a spoon. Within this region, nothing can remain stationary relative to distant observers. The very fabric of space and time is being pulled along by the black hole's rotation. Recent observations have confirmed black holes spinning at significant fractions of their theoretical maximum rates. The supermassive black hole at the center of a distant galaxy rotates at roughly 87% of the speed limit imposed by Einstein's theory of relativity. At this rate, the event horizon completes a full rotation in just a few minutes. These spinning black holes power some of the most energetic phenomena in the universe. Jets of plasma, accelerated to nearly the speed of light, blast outward from the poles of actively feeding black holes. These jets can extend across thousands of light years, carrying energy equivalent to the output of billions of stars. The power source is the black hole's rotation itself, extracted through complex interactions between magnetic fields and the warped spacetime around the spinning event horizon. The process that extracts energy from a spinning black hole reveals another subtle aspect of angular momentum conservation. As energy is drawn from the black hole's rotation, its angular momentum decreases accordingly. The black hole spins down slowly over time, but the total angular momentum of the system is preserved through the motion of the ejected plasma jets. This energy extraction process, known as the Penrose mechanism, demonstrates how angular momentum can be converted into other forms of energy while remaining strictly conserved. The black hole's rotation powers phenomena visible across cosmic distances, but the underlying conservation law ensures that every unit of angular momentum extracted from the black hole appears elsewhere in the system. It's worth pausing to consider how these extreme objects connect to the gentler rotations we observe throughout the universe. The same physical principle that governs a figure skater's spin also determines the behavior of matter falling into black holes. Conservation of angular momentum operates without regard for the violence or gentleness of the physical processes involved. The black holes at the centers of galaxies grew over billions of years through accretion and merger processes, each event carefully preserving the total angular momentum of the system. When two supermassive black holes spiral together and merge, their individual rotations combine according to the strict rules of conservation. The resulting black hole carries exactly the angular momentum predicted by adding the contributions from both original objects. These mergers produce gravitational waves that carry energy and angular momentum away from the system at the speed of light. Recent detections of these space-time ripples have allowed astronomers to measure the spins of black holes billions of light years away, confirming that angular momentum conservation operates even in the most violent events the universe can produce. The gravitational waves themselves transport angular momentum across cosmic distances. When two neutron stars collided 130 million light-years from Earth, the event sent ripples through space-time that carried away a significant fraction of the system's rotational energy. The resulting kilonova explosion scattered heavy elements into space while reducing the total angular momentum of the merged system by exactly the amount radiated away in gravitational waves. These observations reveal that angular momentum can propagate across the universe itself, carried by disturbances in the fabric of spacetime. The waves detected on Earth preserve information about rotational motions that occurred when the universe was significantly younger. In this sense, gravitational wave astronomy allows us to study the conservation of angular momentum across both space and time. Current gravitational wave detectors are sensitive enough to measure the spin rates of merging black holes with extraordinary precision. These measurements test our understanding of angular momentum conservation in regimes impossible to study through any other means. So far, every observation has confirmed that the conservation law operates exactly as predicted, even under the most extreme conditions the universe can produce. As detection sensitivity improves, astronomers expect to observe angular momentum conservation operating on even larger scales. The planned space-based gravitational wave observatory will detect mergers between supermassive black holes, events that transport angular momentum equivalent to the rotation of entire galaxy clusters. These future observations will probe how angular momentum behaves during the largest structure formation events in cosmic history. When galaxy clusters merge, when dark matter halos collide, when the largest bound structures in the universe interact gravitationally, angular momentum conservation governs the outcome with the same precision it shows in laboratory experiments. The cosmic web itself may preserve angular momentum patterns established during the earliest epochs of cosmic history. Computer simulations of structure formation suggest that the filaments of dark matter threading through space carry rotational motions imprinted when the universe was young. These vast currents of rotation, invisible to direct observation, may influence galaxy formation and evolution across billions of years. Some galaxy clusters show evidence of coherent rotation, their member galaxies moving in organized patterns that reflect angular momentum conservation on unprecedented scales. If confirmed, these observations would reveal rotation operating on scales approaching the horizon of the observable universe itself. The persistence of these large-scale rotations connects us directly to the early universe. The angular momentum we observe in distant galaxy clusters was established when the cosmic microwave background was still hot enough to glow. That rotational motion has continued unchanged for most of cosmic history, preserved by conservation laws that operate without exception across space and time. When you look up at the night sky, you're seeing the results of angular momentum conservation operating over billions of years and vast distances. The spiral structure of distant galaxies reflects rotation patterns established when those systems first collapsed from primordial dark matter halos. The orbital motions of binary stars preserve angular momentum from molecular clouds that collapsed when the galaxy was young. Even our local cosmic environment carries angular momentum signatures from ancient interactions. The peculiar motion of our local group of galaxies reflects gravitational encounters that occurred billions of years ago. The Milky Way and Andromeda galaxy approach each other along a trajectory shaped by angular momentum acquired through their shared cosmic history. Current observations suggest that the total angular momentum of the observable universe may be very close to zero. While individual objects and structures carry enormous amounts of rotational motion, these spins appear to be distributed in such a way that they nearly cancel when summed over the largest observable scales. This apparent cosmic balance emerges from countless individual conservation events, each preserving angular momentum with exquisite precision. The universe seems to operate according to principles that ensure both local conservation and global balance, creating a cosmos where rotation persists at all scales while maintaining overall symmetry. The mathematical elegance of angular momentum conservation emerges from the rotational symmetry of space itself. Physical laws remain unchanged regardless of orientation, and this fundamental symmetry automatically leads to conservation through deep connections first understood in the early 20th century. The persistence of rotation throughout the universe reflects the underlying geometric properties of spacetime. Yet there's something almost mysterious about how this abstract mathematical principle manifests as concrete physical phenomena. The spin of electrons, the rotation of planets, the jets from black holes, all emerge from the same conservation law, as if the universe were continuously solving equations in real time. You don't need to understand the mathematical details to appreciate the profound implications. The universe operates according to principles that ensure certain quantities, including angular momentum, can never be lost. This conservation creates a kind of cosmic memory, preserving patterns of motion across billions of years and vast distances. Every rotating object you can observe carries angular momentum that connects it to the cosmic past. The spin of our planet preserves momentum from the solar nebula that collapsed to form our solar system 4.5 billion years ago. The rotation of the Milky Way preserves momentum from the dark matter halo that collapsed when the universe was young. This temporal persistence gives the universe a historical depth that extends far beyond human timescales. The angular momentum we measure today in astronomical objects is the same momentum those objects possessed millions or billions of years ago. Studying rotation allows us to probe the ancient universe directly, reading the signatures of processes that occurred before Earth existed. As you listen to this, consider that your own body participates in this cosmic dance of conservation. The atoms within you carry intrinsic angular momentum, quantum mechanical spin that follows the same conservation laws as galactic rotation. From the smallest scales we can probe to the largest structures we can observe, the same principle operates without exception. The electrons in your neurons, the neutrons in your atomic nucleus, the rotation of the Earth beneath your feet, the orbital motions of our solar system around the galactic center, all participate in the vast network of angular momentum conservation that connects every part of the universe to every other part across space and time. This universality reveals something profound about the nature of physical reality. The principles governing motion operate without regard for scale, complexity, or the passage of time. The same laws that describe a child's spinning top also determine the fate of colliding galaxies, the formations of planetary systems, and the evolution of the largest structures in the cosmos. Tonight, we've followed angular momentum from its gentlest manifestations to its most extreme expressions, discovering a universe where nothing truly stops spinning because the very structure of space and time ensures that rotational motion must be preserved. In this cosmic dance of conservation, we find not chaos, but an underlying order that connects the smallest particles to the largest structures across the vast expanse of space and the deep history of time. The universe spins because it cannot do otherwise, and in that necessity, we glimpse something fundamental about the nature of existence itself. The deeper you dive into angular momentum conservation, the more you realize how it operates in places that seem to defy logic entirely. There are objects in the universe where rotation becomes so extreme that it warps the very nature of space and time around it. These aren't theoretical constructs. They're real, measurable, and they reveal angular momentum conservation, operating at the absolute limits of what physics allows. Consider what happens when you take conservation of angular momentum and push it beyond every boundary we thought existed. beyond neutron stars, beyond the point where matter itself can no longer hold together, lies something that challenges our understanding of reality. A region where the collapse continues past any material limit, where nothing can stop the inward fall of matter toward a mathematical point of infinite density. When this happens, when matter crosses that final threshold and disappears behind an event horizon, the angular momentum doesn't vanish. It becomes something else entirely. It becomes a property of space-time itself, encoded in the geometry of the universe around the black hole. The rotation that once belonged to a massive star now belongs to the fabric of reality. A spinning black hole creates effects that sound like science fiction but emerge directly from the mathematics of general relativity. The rotation drags space-time around with it, creating a region called the ergosphere where nothing can remain stationary relative to distant observers. Space itself is being pulled along by the black hole's spin, like water being stirred by an invisible hand. You can measure these effects from billions of light years away. Recent observations have identified black holes rotating at 87% of the maximum speed allowed by Einstein's relativity. At these rates, the event horizon completes a full rotation in just a few minutes. Matter at the edge of the black hole moves at significant fractions of light speed, held in orbit by gravitational forces that bend light itself. These observations reveal something remarkable about conservation principles. Even when matter disappears from our universe behind an event horizon, the angular momentum it carried remains accessible to measurement. The spin becomes a permanent property of the black hole, preserved for as long as the black hole exists, which may be longer than the lifetime of stars. As you contemplate these extremes, notice how conservation of angular momentum operates without regard for the violence or gentleness of the processes involved. The same principle that governs a figure skater's graceful spin also determines what happens when entire stars disappear into regions where time stops and space curves infinitely. The energy contained in a spinning black hole can power phenomena visible across cosmic distances. Jets of plasma, accelerated to nearly light speed, blast outward from the poles of actively feeding black holes. These jets stretch across thousands of light years, carrying energy equivalent to the output of billions of stars. The power source is pure rotation, extracted from the black hole's spin through processes that operate at the intersection of quantum mechanics and general relativity. This energy extraction reveals another layer of angular momentum conservation. As energy flows out through these cosmic jets, the black hole's rotation slows correspondingly. The total angular momentum of the system remains constant, but it's redistributed between the black hole's spin and the motion of the ejected material. Conservation operates even when matter and energy cross the boundary between our observable universe and regions where physics itself becomes uncertain. The process can continue for billions of years. Black holes at the centers of galaxies have been feeding and spinning for most of cosmic history, their rotation rates carefully regulated by the balance between angular momentum gained through accretion and angular momentum lost through jet production. These ancient objects preserve rotational patterns established when the universe was young. When two black holes spiral together and merge, they create some of the most violent events the universe can produce. Yet even these collisions follow the strict rules of angular momentum conservation. The individual spins of the merging black holes combine according to precise mathematical laws, creating a final black hole whose rotation carries exactly the angular momentum predicted by adding the contributions from both original objects. These mergers produce gravitational waves, ripples in spacetime itself, that carry energy and angular momentum away from the collision at light speed. Recent detections of these waves have allowed astronomers to measure the spins of black holes billions of light years away, confirming that conservation operates even in events so violent they shake the fabric of the universe. The waves themselves transport angular momentum across cosmic distances. When two neutron stars collided 130 million years ago, the gravitational waves from that event carried rotational energy across space for over 100 million years before reaching Earth. The detectors that recorded those waves measured angular momentum that had been traveling through the universe since before complex life appeared on our planet. This temporal persistence of angular momentum reveals something profound about the nature of information in the universe. The rotation measured in those gravitational waves preserves details about objects that no longer exist, carrying signatures of matter and energy configurations that were destroyed in the collision that created the waves. It's worth pausing here to consider the scales involved. The gravitational waves detected on Earth carry information about angular momentum conservation, operating in regimes where matter reaches nuclear density, where space-time curves so severely that time itself slows to a crawl, where the ordinary rules of physics reach their limits. Yet the same conservation law that governs these cosmic catastrophes also operates in the gentle rotation of planets around stars, in the spin of electrons within atoms, in the turning of galaxies through space. The mathematical principle remains identical across scales that span 40 orders of magnitude, from subatomic particles to the largest structures in the observable universe. Current observations are revealing how angular momentum conservation operates on scales approaching the limits of what we can observe. Galaxy clusters, containing thousands of individual galaxies, show evidence of organized rotation that preserves angular momentum patterns established billions of years ago when these structures first collapsed from the cosmic web. Some of these rotating galaxy clusters span tens of millions of light years, their member galaxies moving in coordinated patterns that reflect conservation laws operating on unprecedented scales. The rotation periods involved stretch across hundreds of millions of years, longer than the time between mass extinction events on Earth, longer than the evolution of complex life. These observations connect us directly to the early universe. The angular momentum preserved in distant galaxy clusters was established when the cosmic microwave background still glowed hot, when the universe was opaque to light, when the first stars had not yet formed. That rotational motion has continued unchanged through most of cosmic history. The cosmic web itself may preserve even larger scale patterns of rotation. Computer simulations suggest that the filaments of dark matter threading through space carry rotational currents that influence structure formation across billions of light years. These flows are too subtle and too large to observe directly, but their effects may be visible in the statistical properties of galaxy distributions. If these simulations prove correct, then angular momentum conservation operates on scales approaching the observable horizon of the universe itself. The rotation we observe in the most distant objects may reflect conservation laws that have operated without interruption since the earliest moments after the Big Bang. This universality suggests something deep about the nature of physical law. Angular momentum conservation emerges from the rotational symmetry of space, from the fact that physical laws remain the same regardless of orientation. This mathematical symmetry automatically leads to conservation through connections that link geometry to dynamics, space to time, abstract mathematics to concrete physical phenomena. Yet there's something almost mysterious about how this principle manifests across such diverse scales and contexts. The spin of fundamental particles, the rotation of planets, the jets from black holes, the motion of galaxy clusters, all emerge from the same conservation law, as if the universe were continuously solving the same equation at every scale simultaneously. You don't need to understand the mathematical details to sense the profound implications. The universe operates according to principles that ensure certain quantities can never be lost, creating a kind of cosmic memory that preserves patterns of motion across billions of years and vast distances. Every rotating object you can observe, from the Earth beneath your feet to the most distant galaxies visible in our telescopes, carries angular momentum that connects it to the cosmic past. The spin of our planet preserves momentum from the solar nebula that collapsed 4.5 billion years ago. The rotation of distant galaxies preserves momentum from dark matter halos that collapsed when the universe was young. This temporal persistence gives observations a historical depth that extends far beyond human experience. When you measure the rotation of a distant galaxy, you're observing angular momentum that was established when that galaxy first formed, billions of years before Earth existed. The conservation law has operated without interruption across cosmic time, preserving information about processes that occurred in the ancient universe. As detection methods improve, astronomers are mapping the distribution of angular momentum throughout the observable universe. These surveys soon reveal correlations between rotation, mass, environment, and cosmic history that paint a picture of a universe where angular momentum, established in the cosmic past, continues to influence structure formation and evolution today. Perhaps most remarkably, the total angular momentum of the observable universe appears to be very close to zero. While individual objects and structures carry enormous amounts of rotational motion, these spins seem to be distributed in such a way that they nearly cancel when summed over the largest observable scales. This apparent cosmic balance emerges from countless individual conservation events, each operating with perfect precision. The universe seems to follow principles that ensure both local conservation and global symmetry, creating a cosmos where rotation persists at all scales while maintaining overall balance. The mathematical elegance of this balance reflects deep connections between conservation laws and the fundamental structure of spacetime. The same geometric principles that ensure angular momentum conservation also constrain the total rotational content of the universe, creating natural limits that emerge from the architecture of physical law itself. Current observations suggest that this balance has been maintained throughout cosmic history. As the universe expanded and evolved, as structure formed and galaxies collided, as stars were born and died, the total angular momentum remained essentially constant. The conservation law has operated as a kind of cosmic accounting system, ensuring that every unit of rotational motion gained in one location is balanced by corresponding changes elsewhere. This accounting operates across scales and time periods that challenge human comprehension. When galaxies merge, when black holes collide, when stellar systems form or dissolve, angular momentum is exchanged and redistributed, but never lost. The universe maintains perfect books, tracking every rotation with precision that exceeds any human measurement. The persistence of this cosmic bookkeeping connects every rotating object in the universe to every other rotating object through an invisible network of conservation constraints. The spin of a distant pulsar influences, in some infinitesimal way, the rotation rates available to every other object in the cosmos. Nothing rotates in isolation. Everything participates in the grand balance. As you listen to this, consider that your own motion participates in this cosmic dance. The rotation of the Earth carries you through space at over 1,000 miles per hour. The orbital motion of our solar system around the galactic center carries you at hundreds of thousands of miles per hour. The motion of our galaxy through the local group adds hundreds of thousands more. All of these motions are governed by conservation laws that have operated without interruption since the universe began. The angular momentum that carries you through space tonight was established billions of years ago and will continue unchanged long after the sun has exhausted its fuel and faded to darkness. Yet this vast temporal persistence operates through mechanisms so subtle that you experience it as stillness. The conservation of angular momentum creates stability rather than change, ensuring that the rotational motions we depend on continue without conscious effort or awareness. The Earth's rotation, which gives us day and night, has been maintained for over 4 billion years through conservation laws that operate automatically, requiring no external intervention or maintenance. The orbital motion that gives us seasons follows the same principles, preserving patterns established when the solar system first formed. This stability emerges from mathematical necessities rather than design or intention. The universe conserves angular momentum not because conservation serves any purpose, but because the geometric structure of spacetime makes conservation inevitable. The persistence we observe reflects the underlying architecture of reality itself. Looking toward the future, this conservation will continue operating long after human civilization has passed into history. The rotation of neutron stars will persist for trillions of years, their angular momentum preserved by conservation laws that know nothing of the biological processes that briefly flickered on nearby planets. Black holes will continue spinning in the far future, long after the last stars have exhausted their fuel and faded to darkness. Their rotation will outlast the evaporation of stellar remnants, the decay of protons, the dissolution of atomic nuclei. Angular momentum may be among the last quantities preserved as the universe expands toward its ultimate fate. Even in scenarios where the universe expands forever, becoming increasingly cold and empty, angular momentum conservation will continue operating. Isolated objects will maintain their rotational motion indefinitely, spinning through empty space according to laws that remain unchanged by the passage of cosmic time. This temporal persistence reveals angular momentum conservation as something more than just another physics principle. It represents a kind of cosmic memory, a way the universe preserves information about its past while constraining its future evolution. Through conservation, the present moment connects to the deep history of cosmic time and extends toward an unimaginably distant future. Tonight, we've followed this connection from its manifestation in everyday objects to its operation on cosmic scales, discovering a universe where rotation persists not through effort or intention, but through the mathematical necessities embedded in the structure of space and time itself. The universe spins because it must, and in that necessity lies something profound about the nature of existence. Every rotation you can observe, from the smallest particle to the largest galaxy, participates in this grand conservation, this cosmic dance that connects all motion across space and time through laws that operate with perfect precision and infinite patience. In the quiet persistence of rotation, in the mathematical elegance of conservation, in the vast scales over which these principles operate, we find not answers, but deeper questions about why the universe chooses to preserve some quantities while allowing others to change. Angular momentum endures while everything else flows and transforms, creating islands of permanence in an ocean of cosmic evolution. And perhaps the persistence, that unwillingness of the universe to let rotational motion simply fade away, reveals something essential about the nature of physical reality itself. The story becomes even more profound when you realize that angular momentum conservation reveals something unsettling about the nature of time itself. There are rotational patterns operating in the universe right now that began when the cosmos was young, patterns that will continue long after every star has died and the universe has grown cold and empty. This temporal persistence operates on scales that make human history disappear entirely. The neutron stars we observe today, spinning hundreds of times per second, preserve angular momentum from stellar cores that collapsed billions of years ago. Their rotation connects the present moment directly to epochs when the universe was fundamentally different, when galaxies were smaller, when the cosmic microwave background still glowed hot enough to prevent atoms from forming. You can observe this cosmic memory in action through the precise timing of pulsar signals. These rotating neutron stars sweep beams of radiation across space with such regularity that they serve as cosmic clocks, their pulse periods measured to 15 decimal places. This precision reveals how perfectly angular momentum has been conserved across billions of rotations, billions of years of cosmic evolution. Yet there's something almost eerie about this persistence. The universe forgets almost everything. Stars burn out, planets cool and freeze, galaxies drift apart as space expands. Even protons may decay given enough time. But rotation endures. Angular momentum persists with an almost stubborn determination, as if the universe refuses to let certain patterns fade away. Consider what this means for the deep future. Long after the sun has swelled into a red giant and consumed the inner planets, long after it has shed its outer layers and faded to a white dwarf, the rotational patterns established in our solar system will continue. Jupiter will still orbit the stellar remnant, carrying the same angular momentum it possesses today. The conservation law operates without regard for the biological processes that briefly flickered on nearby worlds. The mathematical elegance of this conservation emerges from something even more fundamental than the laws of motion themselves. Angular momentum is conserved because space itself possesses rotational symmetry. Physical laws remain unchanged regardless of orientation, and this geometric property of the universe automatically leads to conservation through connections that were first understood only in the 20th century. This reveals something remarkable about the relationship between mathematics and physical reality. The universe doesn't conserve angular momentum because conservation serves any purpose or follows any design. Conservation emerges inevitably from the structure of space-time itself, from geometric necessities that operate whether or not conscious observers exist to appreciate them. As you listen, notice how this challenges our intuitive understanding of permanence and change. We expect things to wind down, to gradually lose energy and come to rest. But angular momentum conservation creates islands of permanence in an ocean of cosmic evolution. Certain patterns persist not through effort or intervention, but through mathematical necessity. This persistence operates across nested hierarchies of rotating systems that span the observable universe. Electrons spin within atoms, atoms rotate within molecules, planets orbit stars, stars orbit galactic centers, galaxies move through clusters, clusters participate in the motions of superclusters. Each level conserves angular momentum independently while participating in the larger rotational patterns that contain it. The result is a universe where rotation operates simultaneously at every scale, from quantum mechanical spin to the motion of galaxy clusters spanning hundreds of millions of light years. Yet these diverse phenomena all follow the same conservation law, as if the universe were solving the same equation at every level of organization. Current observations are revealing how this conservation operates in regimes that push our understanding to its limits. When the Laser Interferometer Gravitational Wave Observatory detects the collision of two black holes, it's measuring the redistribution of angular momentum across cosmic distances. The gravitational waves themselves carry rotational energy away from the merger, preserving the total angular momentum of the system while allowing the individual black holes to combine into something new. These detections provide direct evidence that conservation operates even in the most violent events the universe can produce. Two black holes, each containing the mass of dozens of suns compressed into regions smaller than cities, spiral together at significant fractions of light speed. The collision creates distortions in space-time that propagate outward at light speed, carrying precise information about how angular momentum was redistributed during the merger. The waves that reach Earth preserve details about rotational motions that occurred billions of light years away, billions of years in the past. The conservation law has operated across these vast scales of space and time with such precision that scientists can measure the spins of the original black holes from the gravitational wave signals detected on our planet. This temporal and spatial reach of conservation reveals something profound about the nature of information in the universe. The angular momentum we measure today in distant objects carries signatures of processes that occurred when the cosmos was young. Conservation creates a kind of cosmic memory that connects every moment to the deep history of space and time. It's worth pausing here to consider what this universality means for our understanding of physical law. Angular momentum conservation operates without exception across scales that span 40 orders of magnitude, from subatomic particles to the largest structures in the observable universe. No physical system has ever been observed to violate this conservation law. This universality suggests that conservation reflects something fundamental about the nature of reality itself. The principle emerges not from specific mechanisms or interactions, but from the geometric structure of spacetime. As long as physical laws remain rotationally symmetric, as long as the universe looks the same regardless of orientation, angular momentum must be conserved. Yet there's something almost mysterious about how this abstract mathematical principle manifests as concrete of physical phenomena. The spin of electrons, the rotation of planets, the jets from black holes, the motion of galaxy clusters, all emerge from the same conservation law, as if the universe were continuously solving equations in real time. You don't need to understand the mathematical details to sense the profound implications. The universe operates according to principles that ensure certain quantities can never be lost. This conservation creates stability rather than change, ensuring that rotational patterns established in the cosmic past continue to influence events today. Every rotating object you can observe carries angular momentum that connects it to earlier epochs of cosmic history. The spin of our planet preserves momentum from the solar nebula that collapsed 4.5 billion years ago. The rotation of distant galaxies preserves momentum from dark matter halos that formed when the universe was young and dense. This temporal persistence gives astronomical observations a historical depth that extends far beyond human timescales. When you measure the rotation of a distant galaxy, you're observing angular momentum that was established when that galaxy first formed, long before our solar system existed. The conservation law has operated without interruption across cosmic time. The cosmic web itself may preserve rotational patterns from the earliest epochs of structure formation. Computer simulations suggest that the filaments of dark matter threading through space carry subtle currents of rotation that influence galaxy formation across billions of light years. These flows are too large and too subtle to observe directly, but their effects may be visible in the statistical properties of how galaxies are distributed through space. If these simulations prove correct, then angular momentum conservation operates on scales approaching the observable horizon of the universe itself. The rotation we observe in the most distant objects may reflect conservation laws that have operated since the earliest moments after the Big Bang, when the universe was smaller than a proton and hotter than the cores of stars. This connection to cosmic origins raises questions about the ultimate source of all rotational motion in the universe. Current observations suggest that the total angular momentum of the observable universe may be very close to zero. While individual objects and structures carry enormous amounts of rotational motion, these spins appear to be distributed in such a way that they nearly cancel when summed over the largest observable scales. This apparent cosmic balance emerges from countless individual conservation events, each operating with perfect precision. The universe seems to follow principles that ensure both local conservation and global symmetry, creating a cosmos where rotation persists at all scales while maintaining overall balance across the largest structures we can observe. The mathematical elegance of this balance reflects deep connections between conservation laws and the fundamental structure of spacetime itself. The same geometric principles that ensure angular momentum conservation also constrain the total rotational content of the universe, creating natural limits that emerge from the architecture of physical law. As you contemplate these scales, notice how conservation operates as a kind of cosmic accounting system that tracks every rotation with precision that exceeds any human measurement. When galaxies merge, when black holes collide, when stellar systems form or dissolve, angular momentum is exchanged and redistributed, but never lost. The universe maintains perfect books across billions of years and vast distances. This accounting connects every rotating object in the universe to every other rotating object through an invisible network of conservation constraints. Nothing rotates in isolation. Everything participates in the grand balance that ensures total angular momentum remains constant, even as individual systems evolve and change. The persistence of this cosmic bookkeeping will continue operating long after human civilization has passed into history. Neutron stars will continue spinning for trillions of years, their angular momentum preserved by conservation laws that operate automatically, requiring no conscious intervention or awareness. Black holes will maintain their rotation even longer, outlasting the evaporation of stellar remnants and the dissolution of atomic nuclei. Even in scenarios where the universe expands forever, becoming increasingly cold and empty, angular momentum conservation will continue operating. Isolated objects will maintain their rotational motion indefinitely, spinning through empty space according to laws that remain unchanged by the passage of cosmic time. This temporal persistence reveals angular momentum conservation as something more than just another physics principle. It represents a way the universe preserves information about its past while constraining its future evolution. Through conservation, the present moment connects to the deep history of cosmic time and extends toward futures so distant they challenge comprehension. Looking ahead, astronomers expect to observe conservation operating on even larger scales as detection methods improve. The planned space-based gravitational wave observatory will detect mergers between supermassive black holes, events that redistribute angular momentum equivalent to the rotation of entire galaxy clusters. These observations will probe how conservation behaves during the largest structure formation events in cosmic history. Future surveys will map the distribution of angular momentum throughout the observable universe with unprecedented precision, revealing correlations between rotation and cosmic history that span billions of years. These measurements may reveal whether the apparent balance between positive and negative rotations extends to the largest observable scales, or whether subtle asymmetries exist that reflect conditions in the very early universe. As these observations accumulate, they're painting a picture of a universe where angular momentum, established in the cosmic past, continues to influence structure formation and evolution today. The rotation we observe in distant galaxies reflects patterns established when those systems first collapsed from the primordial cosmic web, patterns that have been preserved across most of cosmic history. This preservation operates through mechanisms so fundamental that they emerge automatically from the structure of physical law itself. The universe conserves angular momentum not through design or intention, but through mathematical necessities embedded in the geometry of spacetime. Conservation reflects the underlying architecture of reality. Yet there's something profound about how this mathematical necessity manifests as the concrete phenomena we observe throughout the cosmos. The elegant spirals of distant galaxies, the precise timing of pulsar signals, the jets from black holes, the orbital dance of binary stars, all emerge from the same conservation principle operating across scales that span the observable universe. Tonight, we have followed this principle from its gentlest manifestations to its most extreme expressions, discovering a universe where rotation persists not through effort or maintenance, but through laws that operate with perfect precision across space and time. In the quiet persistence of these rotational patterns, in the mathematical elegance of conservation, we find islands of permanence in an ocean of cosmic change. The universe spins because it cannot do otherwise. In that necessity lies something essential about the nature of existence itself, something that connects every moment to the vast history of cosmic time through laws that know nothing of consciousness or purpose, yet create the stable patterns that make complexity possible. Every rotation you can observe participates in this grand conservation, this cosmic dance that preserves certain quantities while allowing others to flow and transform. Angular momentum endures while everything else changes, creating threads of continuity that stretch from the quantum realm to the largest structures in space, from the first moments after the Big Bang to futures so distant that stars themselves will be ancient history. And in that endurance, that unwillingness of the universe to let rotational motion simply fade away, we glimpse something fundamental about why certain patterns persist while others vanish, why the cosmos preserves some information while forgetting the rest, why in a universe of constant change, some things remain beautifully, mysteriously, eternally the same. The persistence of angular momentum operates with such fundamental authority that it shapes not just what moves, but what can possibly exist in our universe. There are structures spinning in space right now whose rotational periods stretch across millions of years, turning so slowly that entire civilizations could rise and fall between one rotation and the next, yet turning with such precision that their angular momentum has been conserved to extraordinary decimal places across cosmic time. The millisecond pulsars scattered throughout our galaxy represent something almost beyond comprehension. These are stellar remnants, the compressed cores of dead stars, spinning hundreds of times every second with such regularity that they serve as cosmic chronometers. Their pulse timing is so precise that astronomers use them to detect gravitational waves rippling through space-time itself. Yet these objects achieved their incredible rotation rates through a process that unfolds over millions of years. Picture a neutron star in a binary system orbiting close to a normal star. Over eons, matter from the companion star falls toward the neutron star, spiraling inward through an accretion disk. Each particle of infalling material carries a tiny portion of angular momentum with it. As this materials accumulates on the neutron star's surface, it gradually spins the object faster and faster, like a cosmic engine operating over geological timescales. The process can continue for tens of millions of years, each grain of accreted matter contributing its microscopic share of rotational energy to the growing spin of the neutron star. The final result is an object rotating so rapidly that its surface moves at significant fractions of light speed, yet held together by gravitational forces so intense they compress matter to nuclear density. These millisecond pulsars reveal something profound about how angular momentum operates across time. The rotational energy they contain today was accumulated grain by grain, particle by particle, over periods longer than complex life has existed on Earth. Their current spin preserves the cumulative effect of countless individual conservation events, each one infinitesimally small, together creating rotation rates that push matter to its physical limits. As you contemplate these objects, notice how conservation operates simultaneously across vastly different timescales. Each individual particle that falls onto the neutron star conserves its angular momentum in a fraction of a second, but the overall spin-up process unfolds across millions of years. The conservation law operates at both scales with equal precision, connecting microscopic events to macroscopic phenomena across cosmic time. Current observations reveal millisecond pulsars throughout our galaxy, each one a testament to angular momentum conservation operating over these extended periods. Their existence demonstrates that the universe can maintain accounting precision across timescales that dwarf human history, tracking rotational motion with accuracy that exceeds any artificial timekeeper we've ever built. The fastest known pulsar rotates 716 times per second. At this rate, the neutron star completes more than 60,000 rotations every minute. Yet this incredible spin represents the patient accumulation of angular momentum over millions of years, each rotation precisely determined by conservation laws that have operated without error since the accretion process began. There's something almost meditative about these timescales. While human civilizations rise and fall, while species evolve and go extinct, while continents drift across planetary surfaces, these neutron stars continue their patient accumulation of angular momentum, spinning faster and faster according to mathematical principles that know nothing of the biological dramas playing out on nearby worlds. The precision involved challenges our understanding of what accuracy means on cosmic scales. Millisecond pulsars maintain their rotation rates with such stability that astronomers can detect changes of a few parts in a billion. This precision reveals how perfectly conservation laws operate even in the most extreme physical environments the universe can create. But there are theoretical limits to how fast even these objects can spin. Rotate a neutron star too quickly, and centrifugal forces will overcome the gravitational binding that holds it together. The fastest observed pulsars appear to be approaching this theoretical maximum, spinning at rates where the physics of matter itself prevents further acceleration. This speed limit emerges from the fundamental properties of nuclear matter under extreme conditions. As the neutron star spins faster, points on its equator experience forces that eventually approach the strength needed to tear atomic nuclei apart. The star reaches a balance point where further angular momentum cannot be accommodated without destroying the object itself. Recent observations suggest this theoretical limit may be around 760 rotations per second. No pulsar has ever been observed spinning faster than this rate, despite the fact that continued accretion could easily provide enough angular momentum to spin the star much faster. The universe appears to enforce the speed limit automatically, preventing matter from rotating beyond its structural limits. Current models predict that neutron stars approaching this limit might become unstable, either breaking apart or converting some of their rotational energy into gravitational waves that carry angular momentum away from the system. Either way, conservation ensures that the total angular momentum is preserved, even when individual objects reach their physical limits. These limits reveal something important about how angular momentum conservation operates in the real universe. While the mathematical principle allows for arbitrarily fast rotation, physical reality imposes constraints based on the properties of matter and the structure of spacetime itself. Conservation operates within these bounds, creating stable configurations that can persist for billions of years. Beyond neutron stars lie objects where rotation operates at the absolute edge of what physics allows. Black holes can spin at rates approaching the speed of light, their angular momentum encoded in the geometry of spacetime itself. Unlike neutron stars, which are held together by nuclear forces, black holes are constrained only by the structure of space and time. The theoretical maximum rotation rate for a black hole corresponds to the point where the event horizon would move at light speed. At this limit, the black hole's angular momentum reaches a maximum value determined by its mass and the fundamental constants of nature. No known physical process can spin a black hole faster than this ultimate limit. Observations have identified black holes rotating at significant fractions of this maximum rate. The supermassive black hole at the center of a distant galaxy spins at roughly 87% of the theoretical limit. At this rate, the event horizon completes a full rotation in just a few minutes, dragging space-time around with it in ways that create observable effects across thousands of light years. These spinning black holes demonstrate angular momentum conservation, operating at the intersection of general relativity and quantum mechanics. The rotation that once belonged to a massive star now belongs to the curved geometry of space-time itself, preserved for as long as the black hole exists, which may be longer than the lifetime of protons. As you listen, notice how these examples reveal conservation operating across regimes that push our understanding to its limits. From the gradual spin-up of neutron stars over millions of years to the instantaneous formation of rotating black holes during stellar collapse, the same principle governs outcomes across timescales that span 20 orders of magnitude. The jets of material that blast outward from some of these rotating black holes provide another demonstration of conservation in action. These jets can extend across thousands of light years, carrying energy equivalent to the output of billions of stars. The power source is the black hole's rotation itself, gradually extracted through processes that operate at the boundary between classical and quantum physics. This energy extraction reveals how angular momentum can be converted into other forms of energy while remaining strictly conserved. As the black hole powers these cosmic jets, its rotation slows correspondingly. The total angular momentum of the system remains constant, but it's redistributed between the black hole's spin and the motion of the ejected material. The process can continue for millions of years, gradually spinning down supermassive black holes while launching jets visible across cosmic distances. These observations demonstrate conservation operating as a cosmic engine, transforming rotational energy into radiation and particle acceleration on scales that dwarf entire solar systems. Recent gravitational wave detections have revealed another aspect of how conservation operates at these extremes. When two black holes spiral together and merge, their individual angular moment combine according to precise mathematical rules. The collision produces gravitational waves that carry away energy and angular momentum at the speed of light. The waves detected on Earth preserve exact information about how angular momentum was redistributed during these cosmic collisions. Scientists can measure the spins of the original black holes from the gravitational wave signals, confirming that conservation operated with perfect precision even during events so violent they shook the fabric of spacetime itself. These detections represent something remarkable about the reach of conservation laws. Angular momentum that was established billions of years ago in distant galaxies has influenced the gravitational wave signals reaching Earth today. The conservation principle has operated across these vast scales of space and time, preserving information about rotational motion through cosmic epochs. The waves themselves transport angular momentum across the universe. When two neutron stars collided 130 million light-years from Earth, the gravitational waves from that event carried rotational energy across space for over 100 million years before reaching our detectors. The measurement preserves angular momentum that had been traveling through the cosmos since before complex life appeared on our planet. This temporal persistence reveals conservation as a kind of cosmic memory system that connects every moment to the deep history of space and time. The angular momentum we measure today in distant objects carries signatures of processes that occurred when the universe was young, when galaxies were smaller, when the cosmic microwave background still prevented atoms from forming. Current observations are revealing how this memory operates on the largest scales we can observe. Galaxy clusters containing thousands of individual galaxies show evidence of organized rotation that preserves angular momentum patterns established billions of years ago when these massive structures first collapsed from the cosmic web. These rotating galaxy clusters span tens of millions of light years, their member galaxies moving in coordinated patterns that reflect conservation laws operating across unprecedented scales. The rotation periods involve stretch across hundreds of millions of years, longer than the time between mass extinction events on Earth, longer than the evolution of complex life. Computer simulations suggest that even larger structures may preserve rotational patterns from the earliest epochs of cosmic history. The filaments of dark matter threading through space may carry subtle currents of rotation that influence galaxy formation across billions of light years. These flows are too large and too subtle to observe directly, but their effects may be visible in the statistical properties of how matter is distributed throughout the universe. If these simulations prove correct, then angular momentum conservation operates on scales approaching the observable horizon of the universe itself. The rotation we observe in the most distant objects may reflect conservation laws that have operated since the earliest moments after the Big Bang, when the entire observable universe was smaller than a single atom. This connection to cosmic origins raises profound questions about the ultimate source of all rotational motion. Current observations suggest that the total angular momentum of the observable universe may be very close to zero. While individual objects carry enormous amounts of rotational motion, these spins appear distributed in such a way that they nearly cancel when summed over the largest observable scales. This apparent cosmic balance emerges from countless individual conservation events, each operating with perfect mathematical precision. The universe seems to follow principles that ensure both local conservation and global symmetry, creating a cosmos where rotation persists at all scales while maintaining overall balance across the largest structures we can observe. The mathematical elegance of this balance reflects deep connections between conservation laws and the fundamental architecture of spacetime. The same geometric principles that ensure angular momentum conservation also constrain the total rotational content of the universe, creating natural limits that emerge automatically from the structure of physical law. As detection methods improve, astronomers expect to map this balance with unprecedented precision. Future surveys will reveal correlations between rotation and cosmic history that span billions of years, potentially revealing whether the apparent balance extends to the largest observable scales or whether subtle asymmetries exist that reflect conditions in the very early universe. These future observations will probe how conservation behaves during the largest structure formation events in cosmic history, when galaxy clusters merge, when dark matter halos collide, when the largest bound structures in the universe interact gravitationally. Angular momentum conservation governs the outcome with the same precision it shows in laboratory experiments. The persistence of this cosmic accounting will continue operating long after human civilization has passed into history. Neutron stars will maintain their precise rotations for trillions of years, their angular momentum preserved by conservation laws that operate automatically, requiring no conscious intervention or awareness. Black holes will continue spinning even longer, outlasting the evaporation of stellar remnants, the dissolution of atomic nucleuses, possibly even the decay of protons themselves. Their rotation may be among the last quantities preserved as the universe expands toward its ultimate fate, whatever that might be. Even in scenarios where the universe expands forever, becoming increasingly cold and empty, angular momentum conservation will continue operating with perfect precision. Isolated objects will maintain their rotational motion indefinitely, spinning through empty space according to laws that remain unchanged by the passage of cosmic time. This temporal persistence reveals conservation as something more fundamental than just another physics principle. It represents a way the universe preserves information about its past while constraining its future evolution. Through conservation, every moment connects to the vast history of cosmic time and extends toward futures so distant they challenge human comprehension. You don't need to understand the mathematical details to sense the profound implications. The universe operates according to principles that ensure certain quantities can never be lost, creating islands of permanence in an ocean of cosmic change. Angular momentum endures while everything else flows and transforms, creating threads of continuity that stretch from quantum scales to cosmic structures. Every rotating object you can observe participates in this grand conservation, this cosmic accounting that preserves rotational patterns across billions of years and vast distances. The spin of electrons within atoms, the rotation of planets around stars, the motion of galaxies through clusters, all follow the same principle, operating at scales that span the observable universe. As you contemplate these connections, notice how conservation creates stability rather than change, ensuring that certain patterns established in the cosmic past continue to influence events today. The Earth's rotation that gives us day and night has been maintained for over 4 billion years through conservation laws that operate without conscious awareness or external intervention. This stability emerges from mathematical necessities embedded in the structure of spacetime itself. The universe conserves angular momentum not through design or intention, but because the geometric properties of space and time make conservation inevitable. The persistence we observe reflects the underlying architecture of reality. Yet there's something almost mysterious about how this abstract mathematical principle manifests as the concrete phenomena we observe throughout the cosmos. The elegant spirals of distant galaxies, the precise timing of pulsar signals, the jets from black holes, the orbital dance of binary stars, all emerge from the same conservation law, operating across scales that challenge human intuition. Tonight, we have followed angular momentum conservation from its gentlest manifestations in everyday objects to its most extreme expressions in the hearts of dying stars and the event horizons of black holes. We've seen how this single principle governs motion across 40 orders of magnitude, from the quantum spin of electrons to the rotation of galaxy clusters spanning hundreds of millions of light years. What emerges from this exploration isn't just another physics law, but a revelation about the nature of permanence itself. In a universe where stars burn out, planets freeze, and even atomic nuclei may eventually decay, rotational motion endures with an almost stubborn persistence. The same angular momentum that shaped our solar system 4.5 billion years ago continues operating today and will persist long after the sun has faded to darkness. This conservation operates as a kind of cosmic memory, preserving information about the ancient universe in the spin of objects we can observe tonight. When you measure the rotation of a distant galaxy, you're seeing angular momentum that was established when that galaxy first collapsed from primordial dark matter billions of years before our solar system existed. The conservation law has operated without interruption across cosmic time, connecting every moment to the deep history of space and time. Perhaps most remarkably, this principle emerges not from design or intention, but from the geometric structure of spacetime itself. The universe conserves angular momentum because physical laws remain the same, regardless of orientation. This rotational symmetry automatically leads to conservation through mathematical necessities that operate whether or not conscious observers exist to appreciate them. As you listen to this, consider that your own motion participates in this cosmic dance. The rotation of the Earth carries you through space at over 1,000 miles per hour. The orbital motion of our solar system around the galactic center adds hundreds of thousands more. All of these motions are governed by conservation laws that have operated since the universe began and will continue unchanged for billions of years to come. Yet this vast temporal persistence operates through mechanisms so fundamental that you experience it as stillness. The conservation of angular momentum creates stability rather than change, ensuring that the rotational patterns we depend on continue automatically, requiring no conscious effort or external intervention. The universe spins because it cannot do otherwise, and in that mathematical necessity lies something profound about the nature of existence itself.